So the rate of change for a situation describes the dependent variable changes compared to the amount of the independent variable. So I want to highlight a couple of things: dependent variable and independent variable. So for you guys, if you don't have a highlighter, just put rate of change, dependent and independent. What you guys don't realize is that the dependent variable is almost always on the top. So we usually do the dependent variable on the top when we talk about this rate of change over the independent. Okay, so it says consider the Jack and Jill situation. They want us to identify what was the independent and dependent variable or value or parameter. And so remember, we were comparing yards to time, right? It was 4 yards per 3 seconds. Now in this case, we would say that the distance in yards was dependent, because the amount of yards that we went depended on the time that we traveled. So it depended on the time. Now time is an interesting thing because time is almost always independent. So whenever we compare two things, time is almost always independent. So on the Jack and Jill scenario, we said that Jack and Jill went up a hill. They went up 4 yards every 3 seconds. So then the distance was one parameter that we were measuring, and time was the other. Almost always, time is almost always independent. So now for part B, it says identify the rate of change. Well, we said that the rate of change was 4 to 3. Now we say rate of change, right? And I want you to think of these words as being synonymous. In other words, they have the same meaning. Rate of change in most of these scenarios will be what we call the slope of the line. So we're setting up for linear equations talking about the slope of the line. So for question 7, what it says is consider the rate of change and the constant of proportionality and the unit for this situation. What do you notice? Well, what we notice is that the rate of change and the constant of proportionality are basically the same. And Carnegie calls it a unit rate. I don't know if I would call it a unit rate. I'd be very careful with that. But Carnegie is saying they are all the same. You could call it a unit rate if you consider 3 seconds 1 unit of time. Okay, so they're all the same. It's a constant of proportionality because their rate that they travel is the same speed. For every 3 seconds, they're going to go up 4 yards. Okay? Now question 8 says, how would the graph, or how would the rate of change in the graph of the relationship change if Jack and Jill walked faster? How would it change if they moved slower? So let's talk about that. Walking is a measure of distance, right? So let's talk about that. We're measuring 2 things. Distance is a measurement we travel based on how fast we're walking. And then we measured the time, which time just is kind of the same. You know, time is just time. That's why it's almost always the independent variable. So when we say 4 yards per 3 seconds, what happens if I increase the speed? Let's say I do 5 yards to 3 seconds. How would that change the graph? Or slower. So this would be like faster. And I'm using a number, or slower. Slower would be less than 4. So what could I put down for slower? How about 2 yards per 3 seconds? So remember, I don't know if you guys remember this, but this rate of change, this slope, so the rate of change is the same as the slope of the graph. And so if this is larger, so we would say the rate of change as it increases, the graph gets steeper. Now that's an informal word, but I think most of you guys can understand that. As that number increases, then my graph gets steeper. Does that make sense? Hold on, I'm trying to get this to where you guys can see it better. Okay, so as my rate of change increases, then my graph gets steeper. Now what happens, so that's going to occur when we go faster, right? So in this next page, what they want us to do is we're going to look at the graph that shows and represents the relationship between the time Jack and Jill walked and the distance they walked from their home. Let's analyze 3 different moments in time during Jack and Jill's walk to the bus stop. So we're going to look at when the time equals 1, when the time equals 3, and the time equals 6. So now what Mr. Adams did is I highlighted the time when it's 1 second, when it's 3 seconds, and when it's 6 seconds. And then I marked the corresponding distance. Here it is 1.3 yards, here it is 4 yards, and up here it is 8 yards. So when we look at this, we want to think in terms of graphing. It's like x comma y. When we think in terms of the variables, it's the independent variable versus the dependent variable. But in reality, we're comparing time to the distance. In other words, our distance that we travel depends on time. So up here, this part, we're moving over 6, but the 6 represents seconds, and we're moving up 8 where the 8 represents yards. In other words, Jack and Jill moved 8 yards in 6 seconds. Does that make sense? Yeah. So now it says, trace the triangle on a piece of patty paper, label the horizontal and vertical sides on the right triangle with their respective lengths. Now I've got patty paper up here. I'm not going to pass it out to you guys today for time's sake, but what I'm going to do is I'm going to take this patty paper and I'm just going to trace the triangle on the patty paper like they suggested. So I've got this one, and this is 1 and 1.3 repeating. Then I'm going to come over a little bit.
You can write that.
No, don't write it down, just pay attention. Then the next one looks like this. And that is going to be 3 compared to 4. And then the next one is, the last one is 6 seconds. So I'm going to just draw this. And this is 6 and this is 8. So I have these 3 triangles that I've sketched over and traced on patty paper and then labeled their respective lengths. And it says draw right triangles to model these ratios. Then each triangle on a separate piece of patty paper, label the horizontal and vertical sides of the right triangle. And then it says determine the steepness of the triangle by writing the ratio. Now what they're trying to show you is that they're basically all the same steepness. So let me, I kind of goofed and drew 2 on one piece of patty paper, so let me draw this. Now the reason they want me to do this way So I've got 3 triangles, right? I got this triangle, and then I have a third triangle here. Okay? Now, if I want to identify the steepness, what I can do is notice that when I set this triangle on top of this triangle, and this triangle on top of this triangle, they're all the same, which makes sense because they all come from the same graph. But they all have different numbers. So we want to determine the steepness. How do these ratios compare? Well, the reality of it is, remember we said that our rate of change, which is our slope, which is like the change in y over the change in x, is going to be, in our first triangle, it's 1.3, repeating, over 1. And then in our next triangle, we know they're the same because we looked at them. We've got 4 over 3, right? Then in our next triangle, we have 8 over 6. And you'll say, well, Mr. Adams, how do we know all those are the same? Handy dandy calculator. So watch this. What is 8 divided by 6? 1.3 repeating. What is 4 divided by 3? 1.3 repeating. And then if I say 1.33333, oh, I hit the wrong number, or the wrong key. 1.33333 divided by 1, it's basically the same. So they're proportional, right? And so we would say that that is a constant rate of proportionality. Okay? Does that make sense to you guys? Let me leave that up there so you can see it.